Dear students, I just continue with cosmetic analysis and evaluation subject. In my previous class, I have discussed about the various determination of constants, particularly in cosmetic raw materials and finished products. So today, I will talk about the viscosity and other physical constants. Yeah. First of all, what is meant by viscosity? So we all know that you have studied in your degree level B form. Viscosity, it is a quantitative measurement of fluids resistance and quantitative measure of a fluid's resistance to flow. So there are again the different types of viscosity. Viscosities are the dynamic viscosity, kinematic viscosity. Okay, the dynamic viscosity of a fluid is in relative shearing motion, that is an FA given formula. Then kinematic viscosity is defined as a ratio of absolute viscosity to the density of the fluid. So it is viscosity is nothing but shear test by shear rate. So why we should measure the viscosity? So from the viscosity measurement, we can obtain much useful behavioral and predictive information for various products. A frequent reason for the measurement of the rheological properties can be found in the area uh, of quality control, where raw materials must be consistent from batch to batch. For this purpose, the flow behavior, it is an indirect measure of the product consistency as well as the is the reason we measure the viscosity. There are different types. Again, the viscosity measurements, capillary viscometers are there. If you see observe the diagram, so there is a section pulls fluid to start mark, stop mark, capillary section, seconds, and everything. Okay, it gives the kinematic viscosity of the fluid. What is that? Capillary viscometer. It's based on the Paschal's law for steady viscous of flow in a pipe. This is a diagram. Falling spear viscometer is nothing but this type of viscometer. A glass or steel ball rolls down an almost vertical glass tube which is containing the test liquids at a non-constant temperature. So the rate at which a ball of a particular density and diameter falls in an inverse function of viscosity of the minus ds minus s. The figure falling sampling tube. So then another one is the rotational viscometer. So this gives the value of the dynamic viscosity. So it's all based on the principle that the fluid whose viscosity is being measured is shared between two surfaces. So in these viscometers, one of the surfaces is stationary and the other is the rotated by an external drive, and the fluid fills in the space in between. Okay, there are two main types of these viscometers. One is rotational cylinder, rotating cylinder, and cone-on plate viscometers. Cup and bob viscometer. So in this cup and bob viscometers, the sample is sheared in the space between the outer wall of a bob and the inner wall of a cup, to which the bob fits. Okay, so that is then coated type and serial type, and formula is given. The figure, uh, explains there is a stationary cup, sample undergoing shear, a bubble of entrapped air, a drive shaft, a torque set proportional to sharing stress in a sample, and other parameters. RPM, W in grams weight, kV, constant for the instrument, and everything is given. Okay. So rotating cylinder viscometer. If you observe the schematic diagram of a rotating cylinder viscometer, you'll be having a graduated scale and a pointer. Cylinder, one is stationary, inner cylinder stationary, outer cylinder rotating. Uh, inner cannot rotate. Then fluid sample. There is a in center. There is a torsion wire. So the formula is given. Pascals is the dynamic viscosity radii of the inner and outer cylinders radius. Is the shear torque, the angular velocity radius, the immersion depth of the inner cylinder D is the viscometer constant. Cone on plate viscometer. So there is a plate is there is a cone will be the torque spring will be the driving motor will be the test fluid and all. Okay. The formula is given for this. Order flow properties. Next. Fineness of powders. The powder flow properties can be affected by change in particle size, shape, and density. So the flow properties will depend on following. One is the force of friction, another one is the cohesion between one particle to another particle. So the fine particle possesses poor flow by filling void spaces between larger particles, causing packing and densification of the particles. So by using gradient, we can alter the flow properties. How? For example, if you add the magnesium stearate or talc, okay, tangent theta is equal to h by r. Is that so? You take the we all know the what is angle of repose in rheology in physical of pharmacy. Determination of powder flow properties by determining angle of repose that will be measured in degrees. Type of flow, if it is more than 25, it will be excellent. 25 to 30, good. Then 30 to 40, passable, and less more than 40 is very poor. Is less than 25, very good. So by determining angle, a greater angle of repose indicates poor flow. Okay, it should be less. So it should be less than 30 degree and can be determined by following equation. Theta is equal to h by r. Theta is angle of repose, h is height of pile, where r is radius. So bulk density. The bulk density of a powder, it is a ratio of the mass of an untapped powder sample and its volume, including the contribution of the interparticulate void volume. Hence, the bulk density depends on both the density of powder particles and spatial arrangements of particles in the powder bed. So this bulk density is expressed in grams per milliliter because the measurements are made using the. Then what is tapped density? A tap density, it is the term used to describe the bulk density of a powder. After the compression or consolidation, described in terms of tapping the container of a powder a measured number of times, usually from a predetermined height. So the method of tapping, it's the best described as lifting and dropping. So determination of the bulk density, be it apparatus or manually by funnel method, whatever is true density. So the true density or the absolute density of a sample that excludes the volume of the pores and voids within the powder sample. So what are the methods to determine true density? Helium displacement method, that is Photometer. Liquid displacement method, another one. Third one is compression. The figure for helium displacement method. Then liquid displacement method as previous one. Then porosity of the powder. What is porosity? The powder is non-porous, so internal or capillary spaces. The bulk volume consists of true volume and volume spaces between the, that is void. Hence, void volume is nothing but bulk volume minus the true volume. That is V is equal to VB minus VT. That is bulk volume minus true volume. The porosity or void is given by void volume by bulk volume. Okay, that is the formula. Can also be expressed in percentage given by the equation. Then application, it is applied in dissolution. Compare as porous and non-porous, the absorption studies, diffusion of drug, etc. Then determination of the powder flow properties. They are all done by COS index method. It is nothing but cap density minus pore density by cap density. So, it's a very simple, fast, and very popular method of predicting the powder flow characteristics. So, what is this COS index? That means how to determine the powder flow properties. 5 minus 15. So 5 to 15 is nothing but a very excellent type of flow, and 12 to 16 is good. 18 to 21 is very possible. 23 to 35 very poor. Poor 30 to 38 and more than 40 poor. Then those things for the flow properties, density. Okay. Then let's talk about the metals. Heavy metals. A partial list definition in terms of density. Metals which falls naturally into two groups, that is one is light metals, that is density is less than 4, and heavy metals more than 7. Okay, metals having so and so this list. One. Health impacts of the heavy metals in the cosmetic preparation. What is the health hazards of the heavy metals in the cosmetics? So if you look at this table, the metal and its effect, health effect, is the lead is there 0.010 milligrams per liter or ppm. So probable human carcinogen, it means so affect every organ in the body. Okay, so hence the long-term exposure can result in decreased performance and functions of the nervous system, even weakness in fingers, wrists, or ankles. And high lead levels causes damage to the brain, kidneys, and ultimately causes the death also. Right? So in pregnant women, high levels of exposure to lead may cause the miscarriage, and even it will damage the organs responsible for sperm production. So that's about the lead. And arsenic. What is its effect? Health effect. Arsenic. 0.01 mg per L or 0.01 ppm. What is its health effect? Arsenic. Inorganic arsenic is an carcinogen and can cause cancer of the skin, lungs, liver, and bladder. Then lower level exposure can cause nausea and vomiting, but decreased production of red and white blood cells, abnormal heart rhythm, damage to the blood vessels, then sensation of pins and needles in hands and feet. So ingestion of very high levels results in the, okay, that's one. Cadmium 0.005 ppm. Cadmium and cadmium compounds are known human carcinogens. Smokers get exposed to significantly higher cadmium levels than non-smokers. The severe damage to the lungs may occur through breathing high levels of cadmium. So ingesting very high levels severely irritates the stomach, yeah, leads to vomiting and diarrhea. The long-term exposure to lower levels leads to build-up the kidneys and possible kidneys diseases, lung disease, and fragile. Then mercury, it is in that range, that is 0.001 ppm. Mercury chloride and methyl mercury are possible human carcinogens. The nervous system is very sensitive to all forms of mercury, and exposed to high levels can definitely permanently damage the brain, kidneys, and developing fetus. Okay, effects on brain functioning may result in irritability, shyness, tremors, changes in vision, and so on, memory problems. And short-term exposed to high levels of metallic mercury vapors, they may cause lung damage, nausea, vomiting, high irritation, heart rate increase, blood pressure increase. And antimony and its derivatives compounds can definitely adversely affect the skin, lungs, cardiovascular system, and because this antimony is found naturally in the environment, the general population is quite exposed to low levels, primarily in case of food, drinking water, and air. Nickel. So nickel causes allergic reactions when it comes in contact with the skin. So studies on animals shows that if consumed in high amounts, it affects kidneys, stomach, and liver, and other heavy metals. Last one. Example: selenium, barium, chromium. They may present as impurities in cosmetic products. However, the toxicological properties and corresponding risks associated with these substances are considered less significant than for lead, phosphoric, cadmium, mercury, and antimony. The heavy metals can be determined with the help of the following instrumental techniques. One is the atomic absorption spectrophotometer, is atomic emission spectrophotometer, flame emission spectrophotometer, arsenic and heavy metal limit test. This is quite limited, are there. Then atomic absorption spectroscopy, AS. So it deals with the absorption of the specific wavelength of a radiation by the neutral atoms in the ground state. So it's an analytical technique which measures the concentration of the elements, makes use of the absorption of the light by these elements in order to measure their concentration. The neutral atoms are obtained by splitting the sample solution of element using burner like flame. The specific wavelength of radiation is generated by using a hollow cathode lamp. Each metal will get absorbs the light at characteristic frequency. Okay, a zinc at 214 nanometers higher than 248. Okay, cadmium 423, 14589, and so on. So for determination of every element, a separate hollow cathode lamp is required. It's quantity technique. Typical samples, low viscosity samples, is to determine the amount of several metals. Then occasionally can be used as a qualitative technique also. Then the elements can be detectable by atomic absorptions or highlighted in pink in this periodic table. So this is a diagram. There is a radiation source over there and focusing lenses, wavelength selector, then detector, amplifier, and signal processor. So how a sample should be introduced, then atomizer will be there and it goes into this. So where there is a radiation source. The amount of light absorbed by the element is given by the equation. Okay. I square NF by MC. E is charge and the electron, M is mass of the electron, C is speed of light in total number of atoms and cosmic length. How can we obtain the data? The intensity of the light coming through the cathode lamp is measured. The intensity of the light is then again measured and compared to the first result absorbance. The higher the concentration of the metal that is being observed in the sample, the greater the absorbance. Both the light can then be absorbed by atoms from the sample that have vaporized in the flame. This wavelength can then promote the electrons to a higher energy levels. Excited. Atomic spectroscopy with flame. This is diagram. Line of light atomized sample, monochromator, detector, readout. Sample, how to introduce the sample. Yes, sample, readout. What are the various applications? Qualitative analysis, it is applied in qualitative analysis, quantitative analysis, simultaneous multi-component analysis, determination of metallic elements, food and cosmetic industry, emission analysis, miscellaneous applications. Emission flame photometry, we use only deionized water here, not in distilled water, because the distilled water contains too much of amount of this sodium. So clean all glasswares and rinse thoroughly with the deionized water before and after use. So rinse out the plastic wash bottle several times and then fill it up with the deionized water. The equipment needed: 1 500 ml volumetric flask, assorted volumetric flask. So filtration of the solutions is given. Standard calibration procedure. Measure the emission intensity for the blank with deionized water, each standard and unknown. First, you have to light the flame, stabilize the flame photometer. The instrument should have been turned on and the flame lit for 15 minutes to ensure the stability. Then thoroughly rinse all the equipment you use in this experiment. First, lots of distilled water, and secondly, with deionized water from a filled the capped polyethylene vials with the blank, 5 standards, unknown solutions, and place them in the plastic holder designed for them. Then put a glue into a vial, cap it, shake the contents, do this at least 3 times for each vial. So then aspirate the deionized water until the meter reading stabilizes. This may take 30 to 90 seconds. Then use the blank knob to set the meter reading to 000. Then aspirate the highest standards, 5 ppm. The meter reading. Use all the fine sensitivity knobs to set the meter reading. Okay, this is the SOP. And repeat the two-step calibration procedure with again is water and 5 ppm standard as many times as it takes to get them both stabilized at 0.00 and 5. Okay, then aspirate the blank, standards and unknowns that order. Then take 3 replicate readings of each solution once the meet reading has been stabilized. Okay. Then for the second calibration run, place the unknown sample in 2 standards readings brackets that of unknowns, that computational solutions. Aspirated now all increase monotonically. So repeat the whole process of calibration and taking duplicate readings as before, at least for 1 or 2 times. The more data you have to review, the better we'll be able to detect and determinate error inaccuracy in the final reported value. So the heavy metals. The color produced with, in case of heavy metals, with hydrogen sulfide solution is matched against that obtained with the standard lead solution. We all know this with the help of the normal limit test, which you have learned in first year in organic chemistry. Okay, there are 2 necessary cylinders, one for test, one for standard. Then reagents HCl, acetic acid, ammonium hydroxide, hydrogen sulfide solution. Okay, so standard lead solution. Uh, these things should be prepared procedure and all. Here the weigh about 2 grams of material in crucible and heated on a hot plate and then in a muffle furnace to ignite at 16 degrees centigrade to constant mass. Add 3 ml of dilute HCl, warm it, make up the volume, filter the solution, transfer into a Nestle cylinder. Then in the second Nestle cylinder, add acetic acid, 1 ml of lead solution standard, make up the volume with water to 25 ml. Then how to add the hydrogen sulfide solution to each Nestle cylinder and make up the volume with the water to 15 ml because the Nestle cylinder mark will be 50. Mix and allow to stand for 10 minutes. Compare the color produced in the 2 Nestle cylinders. Okay. Then blank determination without samples are recommended to avoid errors arising out of reagents. So results that sample may be taken to have passed the test if the color developed in the sample solution is less than that of the standard solution in the Nestle cylinder. Okay, so these are the reactions with hydrogen sulfide along with acetic acid, lead sulfide, and gas. So in the same way, for determination of arsenic also, uh, we can use the mercury bromide paper, which it will stain yellow in color. Okay, thereby we can compare with that. Arsenic present in a solution material is reduced to arsine, actually, the method, which is made to react with mercury bromide paper. Stain produced is compared with the standard stain. Okay. So, reagents is given ferric ammonium sulfate solution, gases, stannous chloride, Cl. These are various reactions. Okay. This is also as good as the modified gadget test for limit test for the arsenic. Okay. So that means the arsine H3AS4 arsenic acid. Okay, arsenious acid from arsine, then arsine gas ASH3, then mercury chloride paper or mercury bromide paper. Definitely there is an mercury arsenide which stains the yellow. Then we have to compare. Okay, That is how we determine the arsenic. These are the few references. Thank you very much.